In this video, we will be discussing confidence and prediction intervals. At the most basic level, the definition of a confidence interval is a reasonable interval of plausible values for a parameter. The formal definition of a confidence interval looks like this. For some specified probability alpha, we say that the interval L, U is a two-sided 100% times 1 minus alpha confidence interval for parameter theta. If the probability of theta being between the lower limit L and the upper limit U is equal to 1 minus alpha. The upper and lower limits of a confidence interval are random. Hypothetically, if we repeat the experiment and calculations a large enough number of times, each time getting a different interval, roughly 100 times 1 minus alpha percent of the intervals would contain a true fixed parameter theta. For example, if alpha equals 0.05, which is a standard alpha value, your confidence interval would be a 95% confidence interval. And if you repeated that confidence interval experiment 100 times, hopefully 95 of those 100 confidence intervals would contain the true parameter value theta. So most often, confidence intervals are being calculated on the population mean. To calculate a confidence interval of the mean when the population is normal or can be assumed to be normal, you'll need this formula. X bar plus or minus z sub alpha over 2 times sigma divided by the square root of n, where x bar is the sample mean, sigma is the standard deviation. Note that that's sigma, the standard deviation of the population, not the sample standard deviation. And n is the number of observations in the sample. The z-score, z sub alpha over 2, is called a critical value. For normal distributions, you will either need to look these up in the tables in the back of your textbook or use RStudio to calculate them. So the graph here shows the importance of dividing alpha by 2 in the critical value. So for example, if we use the standard alpha value of 0.05, we want to have 2.5%, so alpha over 2 on each side of the graph, which centers our confidence interval around the true mean, theoretically somewhere in the center right here. So let's look at an example in RStudio. We'll call a random sample of data from the normal distribution using the rnorm command as seen in other videos. Again, this command takes 3 parameters: the number of data points, which we'll say is 45 in this case, the true mean, 11, and the population standard deviation, 2.5. So you can see that gives us a data set of 45 data points, hopefully centered around 11 with a standard deviation of 2.5. Now, the z-score. We're going to find a 95% confidence interval on the population mean, where the population is assumed to be normal because of the rnorm command. You'll recall that a 95% confidence interval means an alpha value of 0.05 and an alpha over 2 value of 0.025. We could go to the textbook and look up the z-score for this particular alpha, but it's much quicker to use RStudio. So we'll use the qnorm function and call our variable zval qnorm. So we have an input of 0.975, which is 1 minus 0.025, which is alpha over 2. We could also put in 0.025 in the qnorm function, and it would give us the same thing. So we'll just print that out. And you can see that if we do that for 0.025, we get the same thing, just negative. But in this case, we'll take the positive of the value. This is because the distribution is symmetric when it's standardized. We'll also want to calculate the sample mean of the data set, which again we'll call x bar and use the mean command. Okay, and printing that out, we can see that x bar is equal to 11.02, so very close to our true mean specified in the rnorm command. So now let's plug these into the confidence interval formula. So we're going to name our variables the lower bound of the confidence interval. So that's going to be x bar minus the z value multiplied by the standard deviation, which is 2.5 in this case, and divided by the square root, and that function is just sqrt and r, of 45, our sample size. Okay, and now we can do the same thing for the upper bound. And if you don't feel like typing it out, a fun trick in R is that you can just press the up arrow to see all the commands that you've previously typed. So in this case, we're going to just change the title, the name of the variable and the sign of this. So we want to make it plus. And that gives us both an upper bound and a lower bound. So we'll print those out. And see that our confidence interval is from 10.29 to 11.75. And since we know that the true mean of the data should be 11, it's a relief to see that in a 95% confidence interval, we do contain the true mean. However, you're not always going to be analyzing distributions that are clearly normal. A special case for confidence intervals is when a population is not specified as normal, but has a sufficiently large number of observations, and you can apply the central limit theorem. So this states that when n is large enough, the sample mean, x bar, follows an approximate normal distribution, no matter what the original population looks like, which is a very useful theorem. And so generally, n being sufficiently large means n is more than 40. So this leads to the formula x bar plus or minus z sub alpha over 2 multiplied by the sample standard deviation divided by the square root of n. So you'll notice that in this formula we do use the sample standard deviation because we can't make an estimate of the population standard deviation. So we'll use that. But what happens when your sample size is less than 40? This leads us to using the t-distribution and t-scores in place of z-scores. So even when the distribution is normally distributed, if n is less than 40 and you don't know the population parameter values, like the true population mean and the true population standard deviation, you should be using the t-distribution. And this is because when the sample size is small, the sample standard deviation is much less likely to be close to the true standard deviation. And so this t-distribution takes that into account. The formula for the t-distribution confidence interval is very similar to the z-score formula, as you can see here. The only difference is our substituting a t-score for a z-score, and the t-score not only uses the alpha value, but the degrees of freedom, which n-1. And you'll also use the sample standard deviation instead of the population standard deviation. The other type of interval we will be covering is a prediction interval. Now, a confidence interval tries to predict the true mean value of a population, or some other descriptive statistic of a variable. A prediction interval aims to predict a single value of a variable that will be observed in the future. Again, this type of interval will be using a t-distribution and a t-critical value. This is because your prediction intervals are always wider than confidence intervals. And so therefore the t-distribution must be used. There's a lot more variability in the next data point that could be seen when sampling from a population than there is in predicting a mean value. So the formula for a prediction interval for a single observation from a normally distributed variable looks like this. It's a little bit more involved than the confidence interval formula. Again, you're using the sample mean, the t-score of alpha over 2 and n minus 1, the sample standard deviation, and the sample size n. And your prediction level remains the same. It's 100 times 1 minus alpha percent. So the prediction interval will always be larger than the confidence interval due to the increased variability in prediction errors and estimation errors. So as n gets larger, a confidence interval will shrink until it reaches the true value of mu, or the specified parameter, whereas a prediction interval will approach mu plus minus z sub alpha over 2 times sigma as n gets larger. So as I mentioned, the prediction interval will always be wider than the confidence interval due to the increased variability in prediction errors than in estimation errors. So as n gets larger, a confidence interval is going to shrink until it reaches the true value of mu, or whatever specified parameter, whereas a prediction interval will approach mu plus or minus that z-score sub alpha over 2 multiplied by sigma as n gets larger, because even when you know the true mean and standard deviation, there's always going to be some uncertainty when trying to predict a single value, so that's never going to get very narrow. So we'll do a quick prediction interval example in R. Again, we'll be using the same data set as before, our data set of 45 data points with a true mean of 11 and a standard deviation of 2.5. So for this calculation, we'll need to know the t-value, which we'll name t-val. And in this case, instead of using the q-norm function, we'll be using the qt function. That stands for quartiles of the t-distribution. And again, the t-distribution takes two parameters, the alpha value, which if you'll remember is 0.975, and the degrees of freedom, n minus 1, which in this case is 44. So looking at that gives us a t-value of 2.01. And so we're also going to calculate the sample standard deviation using the SD function, and that's just takes the data as an input. And that gives us a sample standard deviation of 2.5, we'll round up to 2.51, which is extremely close to the actual standard deviation, but that could just be a function of the randomness in this data set. It's not always going to be that close. So now we'll create our prediction interval lower bound using our pre-calculated x bar minus our t-value times the sample standard deviation, and then that is multiplied by the square root of 1 plus 1 over n. A lot of parentheses, but I guess we didn't define n, so we'll do that now. You can define all your variables, or you can input them as hard. I find that defining them in this way allows you to make easy calculations, especially if you're running R from a script. It's easier just to change one variable n that's used throughout the formulas than to go back and change every number hard-coded into your script. So we'll run that lower bound command again, and then we can again change the name to the upper bound and make it x bar plus the t-value times the sample standard deviation times the square root of 1 plus 1 over n. Okay, so we'll take a look at those. Got the lower bound of 5.9 and the upper bound of 16.13. So you'll note that, so our confidence interval, our 95% confidence interval on the true mean of the data was from 10.29 to 11.75, which is very well centered on the mean. It's fairly narrow, which is a good indicator that our data is pretty unbiased. If we look at our prediction interval for the next observation, we see that it's from 5.91 to 16.13, which is much wider, as a prediction interval should be. So, more information on this topic can be found in Chapter 7 of your textbook, Probability and Statistics for Engineering and the Sciences, the 8th edition by J. Devore. Also, a list of RStudio commands used in this video can be found in the video description.